Okay. So a couple days ago we defined something that's very, very important. So f of x is some function. We discovered something called f prime of x. And what was the definition of f prime?
fx plus h minus
No.
Limit.
Oh,
limit.
limit of h.
H approaching 0.
H approaches 0
Of
of f of x plus h minus f of x over h. It was a limit, and was a very important limit. As time goes on, we'll discover just how important this guy actually is. But that allowed us to compute something called a derivative, and this was, remember, the slope of the tangent, so tangent line to function. And this was also called the rate of change of f at x, or we thought of this as how fast f of x is moving at x, or in relation to x. How many times faster is the y value moving than the x value? Whatever the y and x would happen to mean. We also looked at the second derivative and concavity and inflections and all that stuff, like what these will all mean. Now I want to go back to the computational side, because this guy can actually be quite annoying, right? I mean, if we wanted to say f of x equals x cubed, which is a very nice function in general, to figure out what f prime of x would be for this guy, well, this would have to be f of x plus h minus f of x over h, and this will be x plus h cubed minus x cubed over h. Now you have to be able to expand the cube, which, okay, that you might actually know how to do, the x cubed plus 3x squared h plus 3x h squared plus h cubed, right? But now, what if it was the 5th power, the 10th power, the 20th power? Now it starts to get annoying. What if it's actually some really strange power, like 1 over 5, or minus pi, or something? Like this, becomes annoying after a while. And so, of course, this limit is super important, and we appreciate all the work you've done, but sometimes you're just annoying to work with. So, is there a better way? Is the question. And the answer, of course, is yes. So that's what we're going to start talking about. So we know the derivative, we know some reasons why it's important, we know why taking more derivatives can be important, but when it comes to actually computing one, when it comes to actually calculating one for some random function that I'm given, is there a nicer way than actually going through the limit process the whole time? Because it's not hard to see that this can get really annoying for various kinds of functions. And so what we're going to do, so chapter 2 introduced the derivative and some of the reasons why it was important, which we covered last class. So now we're actually going to move into chapter 3, and this is 3.1, and it's actually going to talk about how to compute derivatives. It's going to talk about derivative formulas and properties, I think. Derivative formulas and properties. Yeah, so that's what we're going to do. Figure out some properties of the derivative and some formulas that are going to help us compute them quicker. So let's start with the properties, right? And by properties we mean algebraic properties, like how can we add them, multiply them, divide them, that sort of thing. These are properties. So f of x and g of x are, let's call them differentiable functions, meaning these are functions for which we can find the derivative, we can compute that limit, and it'll actually exist. And c is a constant. Then, 1, it turns out that if I take the derivative of a constant times a function, then that is the same as me taking the constant times the derivative of the function. In other words, constants can factor outside of derivatives, and that's actually not too hard to see. If you look at set g of x equals to a constant times f of x, then your derivative, what is that going to allow? The limit as h approaches 0 of g of x plus h, which is going to be c of x plus h, minus c times f of x all over h. Because constants factor out of limits, that's a property with limits, we can factor out the constant here, and we'd be left with f of x plus h minus f of x all over h, and that's just f prime. So, if you have a constant times a function, you can just factor out the constant and find the derivative of the function. So, for example, we know, because we derived it last time, that the derivative of x squared is 2x. So if someone asks you what is the derivative of 7x squared, well, that's just going to be 7 times the derivative of the x squared. So that's going to be 7 times 2x, it'll be 14x. So with this property, I can tell you, once I know the derivative of a function, I automatically know the derivative of any constant times that function. So this here, this is called the sum difference rule, or the sum difference property. Not the constant factor property. Constant factor. Sum difference property is the next one I'm going to tell you. Constant factor property. Right? We can factor constants out. Okay? So once I know the derivative of a function, I automatically know the derivative of any constant times that function. Here's another important property. It's called the sum difference property. So this basically says, if I want to find the derivative of a sum of functions, so if I'm adding or subtracting two functions, f and g, how can I find the derivative of the sum? It turns out that derivatives distribute across sums. So all I have to do is find the derivative of the f, and then add that to the derivative of the g. Derivatives distribute across sums. That's pretty nice. And of course, if you want to know why, well, set h of h. Suppose we define a function p of x to be the sum of f of x and g of x. What would the derivative of p look like? Well, it's the limit as h approaches 0 of, replace this function with x, the x's with x plus h, minus the original function, all over h. What I can do here is I can group the f's and group the g's. And because it's a fraction over h, I can actually just divide each part by h. And we have a limit property about sums. Limits actually distribute across sums. So I can take the limit of the first part minus the limit of the second part. Plus. And the first part is of course your f prime, and the second part is of course your g prime by the definition. So limits, the derivative will actually distribute across some because the limit distributes across sums. So just a silly example. We'll do a lot more examples of these, but we know at this point that the derivative of x squared is 2x. We also know that the derivative of the square of x is 1 over 2 radical x. So if someone were to ask you, what is the derivative of x squared minus the square root of x. Well, you don't have to go through the limit idea again. All you have to do is just find the derivative of the x squared and subtract the derivative of the square root of x. So it's going to be 2x minus 1 over 2 radical x. So you can find the sum. You can combine the sum and factor rules, of course. So if we have something like, what is the derivative of 5 square root of x plus 7 over x? So you have something like that. Well, that's just going to be the derivative of the 5 square root of x plus the derivative of the 7 over x. Well, here I can factor out the 5, that's 5 times the derivative of the square root of x. Here I can factor out the 7, that's 7 times the derivative of 1 over x. And so this is going to be, well, 5 over 2 radical x. What's the derivative of 1 over x? We also derived that.
1 half to the negative 3 over 2 power.
No, we derived this in class, yeah.
Negative 1 over x squared.
Negative 1 over x squared. We did the limit definition, we calculated that. So we know what that is. So this is going to be minus 7 over x squared. So that would be that answer, right? So knowing how to find the individual derivatives of the radical x and 1 over x, I can figure out the sums of them, and if I multiply any of them by constants, I can automatically figure those out too. So those are nice. Those are the constant factor properties and the sum difference properties. Now, here's another thing that's going to be useful. We'll get back to more properties soon, but here's something that we can know. We can derive, I'm not going to derive it for you, even though we can. We can derive that if I were to take the derivative of the function e to the x, the result would actually be e to the x. Right? So I told you e to the x is a very important function. One of the reasons why it's important is in terms of calculus. Besides 0, it is the only function that is its own derivative. So the rate of change of e to the x is e to the x, meaning if you're on the graph of if you're looking at the graph of e to the x, and you want to measure the slope of the tangent line at any point, the slope of the tangent line is the current y value, right? Which is a very nice property. This, again, you should just know. Not going to derive for you. If you're interested in the derivation, you can watch the 1206 lectures. But at this point, I'm just going to tell you this. I expect you to know this. Derivative of e to the x is going to be e to the x. And another important rule, this is also not something I'm going to derive, but it's super important. So there's an important rule that we call the chain rule. Okay. I'm just going to tell you what it is, not going to derive it. Watch my 1206 lectures if you want to see a derivation. So the chain rule says the following. If I want to differentiate something of this form, f of g of x, the chain rule tells us how to differentiate composite functions. If I take one function and plug it inside of another function, and I have this new function, right? How do I differentiate the composition? Now, here's what the rule says. It says you're going to differentiate the outside function first. Leave the inside function alone. And then you're going to multiply by the derivative of the inside function. So this is the chain rule. So, for example, let's say my f of x is the square root of x. and let's say my g of x is x squared plus 1, then notice that your f of g of x is going to be the square root of x squared plus 1. Now, if someone were to ask you, what is the derivative of the square root of x squared plus 1? Right? How would you actually go about figuring that out, right? One thing you're going to notice is that this is a composition. There is an outside function, namely the square root. And then there's an inside function. The function that I took this function over here, and I plugged it inside of that function. And so the derivative of this, it's the derivative of outer function leave the inner function alone. Sometimes students forget that. Leave the inner function alone in the beginning. So you don't touch the g in the first place, but then you multiply by the derivative of the inner function. Now you have to prove that this actually gives you the slope of this new function, but it does. We're not going to do the proof. So if someone were to ask you to differentiate this, what you're going to do is you're going to notice that this guy here, the square root, is the outer function, and your x squared plus 1, this is the guy that's inside the other guy. Right? So the derivative is going to be differentiate the outer function. How do we differentiate the square root of something? Well, it becomes 1 over 2 times the square root of the thing, right? And what's the thing in this case? Well, it's the x squared plus 1. Right? So this is your g of x, right? So I differentiate around it, but I don't touch it, not yet, right? So I differentiate around it, leaving the inside, but then I multiply by the derivative of the inside. And here I can open up parentheses, and in here, what I'm going to put is the g prime. So now, what is g prime? It is the sum of two things. We have the sum property. So to find the derivative of this, I just find the derivative of one at a time and add them together. What's the derivative of x squared? 2x. What's the derivative of 1? 0, right? Derivative of any constant is 0. So the answer here is 2x over 2 radical x squared plus 1, or the 2's cancel. You get x over the radical of x squared plus 1. That is the slope of this function. So that's a very important rule. That's called the chain rule. So if you have one function inside of another function, you can differentiate the whole overall function by differentiate the outside, leave the inside alone in the beginning, then afterwards multiply by the derivative of the inside. That's called the chain rule. So pretty much everything I told you, we could actually combine So if I were to ask you what is the derivative of the square root of x plus 1 over x all squared, you guys tell me what that is. Do you have an idea here? An answer? Yeah,
negative,
what do you think?
yeah, 2 times x, 1 to this, well, 1 over 2 powers of x. Well, then x to the half power, I guess. Plus x to the negative 1 power times 1/2 x to the negative half power. And then kind of lost there, but it, leave the derivative of x to my negative first power. I'm trying to.
Not, why did you rewrite them?
What happened?
Why did you rewrite it like that?
Well,
So remember the idea is you differentiate the outer function, which in this case is a square,
yeah,
and what do? You leave everything alone. Don't do anything.
yeah, I rewrote it. It was the same thing.
Yeah, it doesn't matter. Why would you rewrite it?
I mean, it's easier for me to see it.
Okay.
And then.
But then you multiply by what? The derivative of the
And then I
inside.
found, yeah, so.
Derivative of this we derived, what is that?
Oh, okay, yeah, that's what I'm saying.
So we should have the formula memorized, yeah?
1 over 2.
1 over 2 radical x was the derivative of that. We derived that. We also derived the formula for this, derivative of 1 over x. What is that? Yeah? Minus 1 over x squared. That would be the derivative. Alright, we derive what the derivative of constant is, what the derivative of x is, what the derivative of x squared, what radical x is, what 1 over x is. So these are things that we know already. So derivative of radical x is 1 over 2 radical x, derivative of 1 over x is minus 1 over x squared. We use the limit definition and figure these out. How do you apply this idea? So my u is some sort of inside function. And in fact, just make it a little more suggestive. Let's at first think of this as some g of x. So my f of x is e to the x. How would you differentiate e to the some function with this chain rule?
Didn't we learn the rule that it equals e to the x, so it would equal e to
Right, so the different derivative of the outer function is just itself, right?
Yeah.
So it's just e to the g of x. But that's not just an x, right? That's an inside function. So what do we do after?
We find the derivative of the outside function.
The inside function.
Oh, okay.
It's like the g is plugged into x, right? It's like you had y equals e to the x, and someone takes another function g, and they puts it inside here,
Okay.
right? So the g is the inside function. According to the chain rule, you'd multiply by the derivative of the inside function, right? So in other words, the derivative of e to some function is the derivative of the function times the original function, right? Or in other words, the rule is usually stated with like u's. So the derivative of e to the u is going to be u prime e to the u. And that's another rule that we know now. So that's memorized. Now, one thing I want you to realize is that that is a more general way to look at it, and it includes this, right? Because if your u were x, your u prime would be what? Well, just 1, right? So it'll look exactly the same. So this is a more general version of that, right? So you don't have to be an x, you can be something else. So for example, if I ask you, what is the derivative of e to the x squared? What would you say? Yeah?
Would be e to the x squared times 2x.
Right. 2x e to the x squared. So, if your e is raised to some random power, the derivative of that thing is the derivative of the power times the original function. And so this, just know this as a rule, because that's pretty important. But the chain rule, also pretty important. And don't worry, it does take some students a while to get used to. That's actually not strange, but we're going to do tons of examples. Like most of next week is going to be us doing a bunch of examples of computing derivatives. So we'll get the practice in, but now I just want to introduce the ideas. Okay. So now, I started off this class talking about, oh, what if we had the x cubed and blah, 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 and blah, blah, blah. How would we find that derivative? So the next question I want to talk about is the derivative of things that look like that. What is the derivative of something like x to a power? Right? So x cubed, x to the fourth, x to the 256, x to the pi, x to some power. How would you find the derivative of such a thing? Right? That is the question. Right? Can we do that in general? Because we don't want to have to go through the limit definition, especially if the power is very large or very weird. What would f of x plus h even mean? How would you even find it? So, here's what we're going to do. Set y equals this function, and of course we want y prime, the derivative is what we're after. Oh, there's something else I need to do. First, we need help. What I'm going to do is figure out the derivative of ln. That's going to help us out here. Because with the ln, I'm not going to have to expand anything. We'll figure out this guy, and then it's going to be easier to figure out that guy, you're going to see. Okay, so if my y is equal to ln x, how can I find y prime? Well, one thing I do is, because I don't know how to deal with the ln, and we all know the trick here, if you have a log and you don't know how to deal with it, use an exponential to get rid of the log. So this means that e to the y is going to be equal to x. Now, we know how to differentiate e to the y. That's this rule. So what we're going to do is we're going to differentiate both sides. Derivative of this is y prime e to the y. By that rule, derivative of x is 1, because we derived that last time. And then I can just solve for my y prime. My y prime is going to be 1 over e to the y. But what is e to the y? Well, e to the y is x. So that's 1 over x. So this means the derivative of ln of x, right, the natural log, is actually 1 over x. Of course, the 1 over x here, you don't have to worry about dividing by 0 because 0 couldn't work in the log in the first place, so your x definitely isn't 0. Your x is some positive number. The derivative of ln x is 1 over x. By the chain rule, we can write the general version of this. The derivative of ln of some function is going to be, of course, 1 over the function times the derivative of the function, right? Derivative of the outside multiplied by derivative of the inside. So this is a new rule. You should know. U prime over u is the derivative of ln of u. So, example. What is the derivative of ln of, say, x squared plus the square root of x plus 1? Well, you're going to take that guy, you're going to put it in the denominator, x squared plus square root of x plus 1. And on top, you're going to put the derivative. So we already derived that the derivative of x squared is 2x. The derivative of this guy is 1 over 2 radical x. The derivative of 1 is 0. That's your answer. In trust me, you wouldn't want to have to do the limit definition on that guy. That would be very annoying. Now let's do this one. The derivative of x to the power. So, we are going to set y equals that function. Of course, we want y prime. And again, we also know that if I have a power that I don't know how to deal with, because if that power is very large, I don't want to have to deal with the power. If I have a power I don't want to deal with, you can use logarithms to get rid of them, right? You can use exponentials to get rid of logarithms. You can use logarithms to get rid of exponentials. So the first thing we do is we log both sides. This allows us to bring the n down in front of us. And then what I'm going to do is I'm going to differentiate both sides. The derivative of ln y by this formula is going to be y prime over y. N is just a constant. The constant factor rule says if I want to differentiate a constant times a function, I leave the constant alone and differentiate the function. The derivative of ln x is 1 over x. So now what I can do is I can solve for my y prime. My y prime is going to be n times 1 over x times y. But what is my y? Well, my y was x to the n. So my y prime is going to be n times 1 over x times x to the n. Now, you have x to the n divided by x to the 1. We know how to deal with that by laws of exponents. You subtract the powers. So this is n x to the n minus 1. Therefore, that's actually the rule. The derivative of x to the n is n x to the n minus 1. That's a very important rule. This is called the power rule. For derivatives. There are other power rules, but this one is called the power rule for derivatives. How do you differentiate something to a power? This is how you differentiate it. Say if you have x raised to a power, that's going to be the power rule. So to go back to the original problem, if I had to differentiate x cubed, right? What is that going to be?
3x cubed. That's squared.
3x squared, right? I take the power, move it down in front, subtract 1 from the power. Right? Or if I had the derivative of x to the 7th, what is that?
7x to the 6th power.
If I had the derivative of x to the minus 4.
4x minus 5.
So now we know how to differentiate x to any constant power. So this is called the power rule. So if you were to do the limit definition of the f of x plus h and expand everything and do all that stuff and plug in h equals 0, you would get nx to the n minus 1 whenever you start with x to the n. And use logarithms to figure that out. So e's and ln's are important for that kind of reason. In the background, they're always kind of help us out. On the face value, we have all these nice formulas. And turns out in calculus, a lot of the time, the background, how we got to those formulas, was through logs and exponentials. So this is called the power rule, very important rule. And of course, we can, through this, let's rederive some formulas. Okay. Now, it turns out, all the formulas that we did before, that we know already, we could actually use the power rule to figure them out, even though we actually derived them the long way. So, we know what the derivative of a constant is. It's 0. it turns out that you could have used the power rule to figure this out. Had you known this rule, what you could do is you could think of this as, this is c times x to the 0. Because x to the 0 is like 1. I can factor out the c and then apply the power rule. This is 0, x to the minus 1. Which is 0. So the derivative constant is 0. We know that the derivative of x is 1. Why is that? Well, that's the derivative of x to the 1 power. Bring the 1 down, subtract 1 from the power. That gives you 1 times x to the 0, which is 1. So we got that again, pretty easy. Derivative of the square root of x. We did that using the limit definition. We had to multiply and divide by the conjugate, simplify all sorts of stuff. We ended up with 1 over 2 radical x. Turns out we could have thought of this in terms of the power rule, x to the 1/2, and then bring the 1/2 down, subtract 1 from the power. You get 1/2 x to the minus 1/2, which of course you can rewrite as that by the laws of exponents, which gives us back the original. So everything I told you before, we could actually figure out here. So what is the derivative of 1 over x? Well, you could have written it as x to the minus 1 with the laws of exponents, and then using the power rule, bring the minus 1 down, subtract 1 from the power, you get minus x to the minus 2, which is of course minus 1 over x squared. So everything we kind of knew all this already, but you could actually derive them using the power rule. So the power rule is a very important rule, and of course, this is going to be the main idea. Whenever you see anything like any radicals or anything going on with x's, probably the best strategy that you're going to want, you can rewrite it as a power. If it's not a rule that you automatically have memorized, rewrite it as a power and apply the power rule. So what if I ask you, what is the derivative of the cube root of x? How do you find the slope of the tangent line to that function?
One-third x to the negative 2/3 power.
Well, how did you think about it?
So I rewrote it, so it would be x to the 1/3
So
power.
1/3. So that's the cube root.
And then I subtracted the power by 1. And then I moved the power to the front.
Yeah. 1/3 minus 1,
Negative 2/3.
negative 2/3. Because you think of the 1 as 3 over 3. So 1 over 3 minus 3 over 3, you get minus 2 over 3. So that's actually the derivative. By the way, the conjugate of the cube root isn't really very pretty. It has 3 terms, not 2 terms. So yeah, or you can write it as 1 over 3 x to the 2/3, or you can write this as, I mean, that's fine for me, but, or these are all equivalent ways to think about it, the cube root of x squared. So yeah, if you were to do the limit definition, the cube root of x plus h minus the cube root of x all over h, multiplying that by the conjugate would actually look pretty weird. The conjugate would look like x to the 2/3 plus x to the 1/3 plus h or something like that. Like you actually did that formula where you had, say, x cubed minus a cubed is equal to x minus a x squared plus ax plus a squared. So you use the difference of cubes formula. So if you want to cube both things, you multiply by something that looks like this. So if you had like a cube root of x here, so you can imagine that the cube root of x, if you put 1/3 power on each of those, then you'd have just a 1 power in each of these, and it'll allow you to cancel the h, it'll work out. So you'll get x to the 2/3 plus x plus 1, if there was a 1 here, but the h, you can replace the a with h. And you can actually try it, but not too interested in doing that. So once you start get weird powers, once it's not a square root, the square roots are easy. The conjugate is just those two terms you change the middle sign. Once you start getting cube roots, 4th roots, 5th roots, the conjugate starts getting longer. The conjugate of a 5th root has 5 terms in it. The conjugate of a 7th root has 7 terms in it. They start getting really annoying to work with. So, luckily with the power rule, we never have to work with it. We just rewrite it as a power and do it. Let's apply a previous rule that I spoke about. Let's make sure we know how to do that. What is the derivative of? The derivative of that. And in the meantime, I'll give you some stuff to think about over the weekend. And you can tell me what you came up with on Tuesday. We're pretty much next class, and I don't know, might spill over to the following class. We're going to be finding these guys. Find the derivative of. Did anyone come with the answer for that one?
Almost
What did you get?
15x squared minus 3 over 2 times square root of x.
Mm-hmm. This
And
one?
then- And then that one I haven't.
Did anyone do this one?
I didn't get that.
Yeah?
Is it minus 4/3 x to the negative 4/3?
How did you get that? What did you think of this as?
4x to the negative 1.
This is 4x to the minus 1/3. Bring the minus 1/3 down, you get minus 4/3. Subtract 1 from the power. That's minus 1/3 minus 3/3, you get minus 4/3. Yeah, that's actually the answer. Okay, try these. And fair warning, some of these are going to require rules that I haven't mentioned yet, but at least maybe you can identify what those are. So try those. We have like 20 examples for this section, but that's the first 7. See where you can get with those.